Tonight, on Space Science, a spacecraft is about to leave Earth not to land, but to prove that humans can travel farther than they have in over 50 years. Artemis II is not just a mission, it is a test of distance, precision, and survival in deep space. From the moment Orion ignites atop the most powerful rocket ever built, every second becomes a step away from Earth and toward the Moon. No landing, no margin for error, just a single, sweeping arc around another world, and the long journey home. If you're fascinated by how humanity returns to deep space, follow the mission with us, like the video, subscribe to Space Science, and stay with the journey from Earth to the edge of the Moon and back again. Earth holds human spaceflight within a narrow range of habitability and familiarity. It supplies air, pressure, liquid water, magnetic shielding, and the steady pull of gravity that shapes every human body from birth. From the ground, space often appears as a single upward direction, but from an engineering point of view it begins as a series of boundaries that grow harsher with every increase in altitude. The atmosphere thins, temperatures swing more sharply, and the conditions that support ordinary life fall away layer by layer. Even after a spacecraft rises above the dense air, Earth still dominates the journey. Its gravity governs ascent, orbit, return, and survival. Its oceans, weather systems, continents, and clouds remain close enough to define the view from the window and the logic of mission design. In this broadest sense, the story of the farthest human travel from Earth begins not with distance itself, but with the simple fact that almost all human movement in space still happens inside Earth's physical and protective domain. That is the normal condition of crewed flight. It is the background against which rare departures are measured. Most astronauts who leave Earth do not go very far from it in cosmic terms. They enter low Earth orbit, circle the planet, and remain inside a region where home is still visually immediate and physically near compared with the scale of the solar system. The International Space Station, for all its technical difficulty and scientific importance, still belongs to this close orbital neighborhood. Rescue is difficult there, but the journey remains fundamentally Earth-centered. Communication delay is slight. The planet fills much of the outward view. Return takes hours rather than days. Through the long history of human spaceflight, this near-Earth region becomes the main arena of experience, work, and risk. Even crews who spend months away from the surface are, in a strict spatial sense, still almost resting against the planet when measured against the distance to the Moon. The gap between low Earth orbit and cislunar space is not a small extension of the same trip. It is a change in category, in scale, and in consequence. Through that contrast, Earth becomes more than the place beneath the spacecraft. It becomes the dominant center of human flight history. Only the Apollo crews travel far beyond that center, and they do so during a brief period in the late 1960s and early 1970s, since Apollo 17 returns. No human mission leaves low Earth orbit for more than half a century. This long confinement gives Earth an even stronger role in the history of exploration. It is not only the origin of every crewed mission, it is also the sphere that human beings, for the most part, do not yet leave. The Apollo missions therefore stand as an exception inside the larger record, not as the start of a steady outward expansion. Their crews pass into the broad region between Earth and Moon, and then the species returns to orbital operations close to home. That long return to near-Earth flight quietly reshapes expectations. Earth once again becomes the ordinary horizon of human space activity, while deep space travel remains a memory rather than a continuing practice. For that reason, Artemis II stands apart. NASA describes it as the first crewed Artemis flight, a lunar flyby mission aboard Orion, launched on the first day of April in the year 2026 for a journey of about 10 days around the Moon and back to Earth. In the history of human flight, that makes it unusual before any later milestone is reached. It does not merely circle Earth, and it does not travel to an orbital laboratory. It resumes a category of human voyage that has been absent since the Apollo era, a mission that carries a living crew outward toward deep space, away from the close visual and operational comfort of near-Earth flight. NASA materials also state that the mission is intended to carry its crew beyond the farthest distance reached during Apollo 13, if the planned path continues as designed. Even before that threshold is crossed, Earth remains the central fact of the mission's meaning. Artemis II is remarkable because it begins at the edge of the ordinary human range and points away from the region that has contained almost every astronaut in modern history. Earth's importance in this opening region is not symbolic alone. It is physical, operational, and biological. Every system aboard a crewed spacecraft is built as a temporary replacement for what Earth provides naturally. Cabin pressure stands in for the atmosphere. Stored water stands in for rivers and clouds. Thermal control replaces the moderating effect of a planetary environment. Radiation protection becomes a managed engineering concern rather than a quiet atmospheric gift. Food, waste handling, sleep cycles, and medical monitoring all become deliberate spacecraft functions because the crew is leaving the only world known to support human life without machinery. That truth becomes sharper as missions move farther from Earth, but it is already present at departure. The farther humans travel, the more clearly Earth is understood not as a backdrop but as an active life support system on a planetary scale. From this widest vantage, the mission's distance record is only one measure among several. Another is separation from the dense network of natural protections that Earth supplies without effort. This is why the opening layer of the mission is best understood through scale and rarity. Earth is large enough to hold every human landscape, every sea route, every desert, every city, every launch site, and every recovery zone. Yet in spaceflight history it has also functioned as a boundary that humans almost never cross in a deep sense. A crew may leave the ground often. It may even remain in orbit for months. Still, true departure from Earth as a nearby world remains uncommon. The Apollo missions prove that such travel is possible. Artemis II, now in flight, restores that outer category of travel to human experience. It does so not by diminishing Earth, but by showing how completely Earth has contained human movement until now. The planet remains the reference point for every measure that follows distance, time, risk, visibility, communication, return. In that calm and literal way, Earth forms the first region of the story. It is the homeworld, the protective shell, the gravitational center, and the standard against which the farthest human journey is defined. The launch corridor begins on the ground, while the vehicle is still motionless and the crew is still inside a machine that has not yet become a spacecraft in flight. At this stage, the journey is defined by alignment, timing, weather, and geometry. The rocket stands upright at the pad as a fully assembled path rather than a single object. Its tanks hold propellants at very different temperatures. Its structure carries the spacecraft, the abort tower, the upper stage, and the crew module in one vertical line that exists for a brief period only. Once the engines ignite and the solid boosters light, that line becomes motion, noise, and acceleration. Before that moment, however, the launch corridor is a narrow window of permission created by Earth itself. Winds at different heights, electrical conditions in the air, cloud layers, sea state for recovery support, the readiness of tracking systems, and the exact relation between launch time and the desired parking orbit all matter together. The corridor is not merely a direction into the sky. It is a temporary agreement between vehicle performance and the changing state of the planet around it. From the pad, the vehicle does not rise through empty space. It must first cross the lowest and heaviest part of Earth's atmosphere, where dense air resists motion and amplifies stress. This is why the opening minutes of ascent are shaped by both power and restraint. The rocket must accelerate strongly enough to climb and gain speed, but it must also manage aerodynamic load, vibration, and structural bending. The atmosphere pushes hardest when speed has grown large while the air is still relatively thick. Engineers call this region of peak aerodynamic stress max Q, a short term that refers to the moment when the dynamic pressure on the vehicle is greatest. In physical terms, it is the interval when the rocket passes through the harshest combined pressure of air and velocity. The launch corridor, therefore, has an internal climate of its own, a changing sequence of forces that the vehicle crosses in order. The crew experiences this not as visual drama alone, but as vibration, sound conducted through the structure, and the steady growth of acceleration pressing them into their seats. The corridor is also geographic. A launch does not point straight upward and remain there. It bends downrange, turning altitude into orbit by building horizontal speed as well as height. The Earth below remains part of the calculation throughout ascent. The target parking orbit has a specific inclination, meaning a specific tilt relative to the planet's equator, and the launch time must match the moment when the rotating Earth places the launch site under the needed orbital plane. This is one reason launch windows matter so precisely. A crewed lunar mission is not simply waiting for good weather. It is waiting for Earth's rotation, the launch site, the performance of the rocket, and the desired early orbit to line up in the same brief interval. In that sense, the launch corridor is carved by celestial mechanics, even while the rocket is still within the atmosphere. Ascent proceeds through distinct physical transitions, though from inside the crew cabin they may blend into one continuous rise. The core stage engines ignite first and reach stable operation before the solid boosters take over with overwhelming thrust. Once the vehicle leaves the pad, the surrounding world changes quickly from tower, flame trench, and coastal ground systems to cloud layers, blue curvature, and thinning air. The abort system remains active during the early ascent because the vehicle is still in the phase where a rapid separation of the crew module from the rest of the stack must remain possible if the booster fails. This makes the launch corridor not only a route upward, but also a region of escape logic. The crew rides through a period in which the spacecraft above them is attached to a launch system powerful enough to carry it away from danger at short notice. As the vehicle climbs higher, the character of resistance changes. Air becomes thinner, aerodynamic forcing falls away, and the rocket's motion begins to resemble orbital insertion more than atmospheric ascent. By then, the first great surge of booster thrust has passed. Staging events separate emptied hardware from the still-rising vehicle, and the stack becomes progressively lighter. Each discarded element marks a transition in the corridor from brute lift to more refined acceleration. The ascent path remains carefully shaped because the goal is not to go as high as possible as fast as possible. The goal is to place the crewed spacecraft into a stable temporary orbit around Earth with the correct energy, the correct attitude, and the correct system status for further mission operations. Parking orbit is therefore not an incidental pause. It is the intended endpoint of the launch corridor itself. The launch succeeds not when the rocket leaves the pad, but when the spacecraft has been delivered into that planned Earth orbit in a condition the crew and controllers can trust. Inside the cabin, this corridor compresses Earth into sequence. There is the moment of ignition, the release from the pad, the rough passage through dense air, the easing that comes as the atmosphere thins, the shifting pattern of stage events, and then the quiet change into orbital flight. Weight and force vary across these minutes. The body feels heavy under acceleration, and then briefly light at separation events. The view outside shifts from ground structures to sky, from sky to darkness, from a local horizon to the broad curve of the planet. Yet Earth never leaves the scene. Its air resists the climb, its gravity pulls on every stage of motion, its rotation helps determine the launch moment. Even the achieved orbit is still a close attachment to the planet, a path of falling around Earth rather than away from it. So this second region of the journey remains entirely within Earth's immediate grasp. The launch corridor is the narrow path through atmosphere, pressure, timing, and gravity that turns a grounded vehicle into an orbiting one. It is violent in energy yet exact in design. It depends on immense thrust, but it also depends on restraint, alignment, and timing measured with care. For the crew, it is the crossing from surface life into orbital motion. For Earth, it is a brief release, not yet a farewell. The planet still fills the mission's logic from beginning to end in this phase, shaping the route upward and defining the temporary orbit that closes the ascent. Once Orion reaches its temporary orbit around Earth, the character of the mission changes at once. The violence of ascent gives way to a quieter condition, in which motion continues, but force no longer arrives through constant thrust. The spacecraft is now in free fall around the planet, moving fast enough sideways that the ground curves away beneath it as quickly as it falls. This is the ordinary condition of orbit, but for a crewed lunar test flight it also becomes a period of inspection, confirmation, and adjustment. Orbit provides time to determine whether Orion is behaving as a complete spacecraft, rather than merely as a payload that has survived the ride upward. In this narrow band around Earth, close enough for rapid communication and constant tracking, the crew and flight controllers begin the careful work of turning arrival into readiness. The first reality of this phase is that orbit is not rest. The cabin may feel weightless, but the spacecraft remains a dense assembly of systems that must be understood in their new environment. During ascent, vibration, acoustic stress, stage separations, and changing acceleration have passed through the structure. Components that performed correctly on the pad and through powered flight must now prove that they continue to function in stable orbital conditions. Electrical systems are checked for expected output and distribution. Computers are compared against planned states. Sensors are examined to confirm that the spacecraft knows its attitude, its power condition, its thermal balance, and the health of its internal equipment. A test flight gains much of its value here, in the quiet verification that the machine now behaves as designed when left to sustain human beings in space, rather than merely to survive launch. The orbit itself provides a useful setting for this work because Earth remains nearby in every operational sense. Ground stations and tracking networks follow the vehicle through relay systems. Communication delay is slight. Mission Control can compare onboard readings with external tracking data and with the expected performance profile built before launch. The crew, in turn, can move deliberately through procedures without the harsher time pressure of ascent. They observe displays, inspect cabin conditions, and confirm that the spacecraft interior supports normal work. In microgravity, loose objects drift, body movement changes, and every action requires a different kind of control than on the ground. This is a nearby proving ground in which people and spacecraft learn one another in orbit. Life support verification becomes especially important during this interval. On Earth, breathable air, temperature moderation, and waste removal are so constant that they are rarely noticed. Inside Orion, each becomes a system that must be monitored. Cabin pressure must remain stable. Carbon dioxide must be removed efficiently. Humidity and temperature must stay within acceptable limits. Water management, food storage, lighting, and the arrangement of equipment all matter because human performance depends on ordinary bodily comfort more than spaceflight language sometimes suggests. A crew cannot assess the spacecraft well if the spacecraft is not already proving that it can protect sleep, breathing, orientation, and clear thinking. So the orbital checkout is partly technical and partly biological. It confirms not only that instruments and valves respond correctly, but that the crew can inhabit the cabin as planned. Power production and thermal control also move to the foreground in this region. Orion depends on electrical power for avionics, communications, cabin systems, and many layers of control. Its solar arrays must deploy and track properly, generating the expected energy while the spacecraft changes attitude and passes through cycles of sunlight and shadow. Batteries must charge and discharge within planned bounds. At the same time, heat must be managed. Space is not cold in a simple uniform way. Surfaces in sunlight absorb strong radiant energy, while shaded areas lose heat rapidly by radiation. Thermal control therefore becomes a balancing act of insulation, circulation, radiators, heaters, and operational choices. Temporary Earth orbit offers an excellent place to verify that the spacecraft can hold this balance under real orbital lighting conditions, while support from the ground remains immediate. Guidance and navigation checks belong to the same broad purpose. Orion must know where it is, how it is oriented, and how accurately it can change that orientation. Star trackers, inertial sensors, software estimates, and ground-based tracking together form the spacecraft's sense of place. In parking orbit, these sources can be compared carefully. Small thruster firings may be used to test response, trim attitude, or verify control logic. Such firings are modest compared with ascent, but they are essential because a crewed spacecraft is never defined by structure alone. It is defined by controlled motion. The ability to point correctly determines communications, power generation, thermal management, window views, and crew tasks. The human crew adds another dimension to this phase. After launch, the astronauts transition from ascent posture to orbital routine. They secure floating items, configure displays for mission operations, and begin the measured rhythm of living inside the cabin. They also serve as observers whose senses complement the telemetry. A smell, a sound, a vibration, or a stiffness in a latch can matter. Human presence is not secondary to the spacecraft test. It is part of the test. Orion is being evaluated as a crewed vehicle, not as an empty capsule. The astronauts therefore assess habitability, reach, lighting, noise, workflow, and the ordinary sequence of movement through the cabin. Outside the windows, Earth continues to dominate the scene. Continents, oceans, cloud systems, and the thin brightness of the atmosphere pass below in repeated cycles. Day and night alternate quickly as the spacecraft circles the planet. This repeated return of Earth beneath the vehicle gives the checkout phase a particular psychological quality. The crew is already away from the surface, yet still fully within the visual authority of the homeworld. Every orbit renews the sense that this is still Earth flight. In operational terms, that closeness is an advantage. It allows the mission to examine the spacecraft where help in understanding is strongest, and where the difference between a minor anomaly and a major concern can still be judged against the familiar backdrop of near-Earth space. So this third region is a pause in motion without being a pause in work. Temporary orbit serves as a proving band wrapped around the planet, a place where Orion and its crew determine whether the spacecraft functions as a living system. Earth remains close enough to support measurement, communication, and perspective. The spacecraft remains busy with verification rather than with transit. In this zone above the world, the mission turns ascent into confidence. The departure from Earth orbit does not happen at launch, and it does not happen merely because Orion is already in space. It happens later, in a more deliberate way, through a controlled engine firing that changes the meaning of the mission from orbital flight to lunar travel. Until that moment, the spacecraft still belongs to the near-Earth region. It circles the planet, remains fully within its gravitational control, and can still be described as an Earth-orbiting vehicle. The departure burn changes that condition. It adds the energy needed to stretch the spacecraft's path outward until the Moon becomes part of the immediate flight geometry. In mission language, this is the translunar injection burn. In physical terms, it is the act of reshaping motion. Orion does not rise onto a road already waiting in space. It must be placed onto that road by propulsion, timing, and exact direction. Before the burn begins, the spacecraft must already be in the proper orbital arrangement. That requirement gives this phase its quiet seriousness. The crew has completed its early checks in Earth orbit, and Mission Control has examined the vehicle's condition with care. The orbit itself has been adjusted into the geometry needed for departure. The spacecraft attitude must be correct. The main engine system must be ready. Guidance, navigation, and control must agree on where Orion is, how it is pointed, and how the burn will be measured. This is a more focused kind of readiness than the general readiness of launch day. The launch proves that the crew and spacecraft can leave the surface and reach orbit. The translunar injection burn proves that the mission can truly begin its outward journey. The engine used for this change belongs to Orion's service module, the section that provides propulsion, power, and key support functions for the spacecraft. During the burn, that engine fires for several minutes, long enough to deliver a major increase in velocity. The change is not dramatic to the eye in the way a terrestrial launch is dramatic. There is no tower falling away, no dense atmosphere streaming past the windows, no rising column of fire against the ground. Instead, there is a sustained push in weightlessness, a measured period of acceleration in silence except for the internal sounds of the spacecraft. Yet in mission terms, this quieter event carries enormous significance. It is the last major main engine firing of the mission, and it effectively decides that the crew is no longer staying close to Earth. NASA describes it as the burn that sends Orion toward the Moon and places the spacecraft onto its free return lunar path. The outward journey, and in an important sense the return as well, are both shaped here. The timing of the burn matters as much as its strength. In orbital mechanics, where a spacecraft is along its orbit when propulsion is applied, determines how efficiently the change in speed alters the path. The translunar injection burn is therefore not simply a long thrust delivered whenever the crew is ready. It must occur at the correct point in the orbit and in the correct direction relative to Earth and the Moon. Earth's gravity remains the dominant force during the firing, and the burn works with that geometry rather than against it. A small error in timing or direction at this stage would not produce a dramatic visible failure at once, but it would change the path across the long distance ahead. That is why such burns are executed through precise targeting and close monitoring, with spacecraft software, crew procedures, and ground calculations all aligned around the same intended result. Inside Orion, this is the first moment when distance begins to feel committed rather than possible. Parking orbit still allows a psychological sense of circling near home. The planet repeats beneath the spacecraft. The mission remains visually Earth-bound. During the translunar injection burn, that repetition ends. The spacecraft is no longer preserving a closed loop around Earth. It is lengthening its path into an open outward arc. The acceleration is modest compared with launch, but the significance is greater because there is no immediate return to the same orbital rhythm. After the burn, each minute carries Orion farther from the region in which humans have spent nearly all of their time in space. The burn also reflects the unusual discipline of lunar mission design. It is not enough to head toward the Moon in a broad sense. The spacecraft must leave Earth with the right energy for the planned lunar flyby, the right geometry for lighting and power conditions, and the right overall path for later return to Earth. NASA planning documents describe Artemis II as using a free return profile, meaning a trajectory that uses the Earth-Moon gravitational arrangement so that, after passing the Moon, Orion naturally bends back toward Earth rather than requiring a large engine burn to begin the homeward leg. That does not eliminate the need for later smaller correction burns, but it makes the translunar injection burn especially important because so much of the overall mission shape is embedded in it from the start. From the crew's point of view, the event is both technical and historical. It is technical because it demands observation, procedure, and trust in the spacecraft's propulsion system. It is historical because it marks the return of a human crew to deep space departure after more than half a century without such missions. The burn is the dividing line between revival and repetition. Before it, Artemis II still shares something with earlier Earth-orbiting missions. After it, the mission belongs to the rare category of human voyages that truly leave Earth orbit behind. So this fourth region is a hinge between closeness and distance. It lasts only minutes, but it changes the scale of the entire journey. The translunar injection burn is a controlled act of commitment, carried out with precision rather than spectacle. It turns an orbit into a path, a spacecraft into a traveler, and a near-Earth mission into a lunar one. After the translunar injection burn, Orion no longer behaves like a spacecraft repeating a familiar path around Earth. Its motion is now an outward coast, a long falling curve that carries the crew deeper into cislunar space while the planet recedes behind them. In this phase, nothing dramatic seems to happen in the visual style of launch or engine firing. The spacecraft is simply there. Stable and move changes profoundly in this interval. Earth is still the point of reference for every calculation, every communication link, and every human thought aboard the vehicle. But it is no longer the surrounding world. It becomes a destination behind the crew, rather than the immediate setting around them. The first sign of this change is visual. In low Earth orbit, the planet fills much of the window with cloud systems, ocean color, and the bright curved line of the atmosphere. Surface detail passes quickly because the spacecraft circles the world in short repeated loops. On the outbound coast, that pattern disappears. Earth no longer returns beneath the vehicle every 90 minutes. It stays in one general direction and slowly grows smaller. Continents become less legible. Weather systems merge into broad white swirls. The atmosphere, so striking in near orbit as a narrow blue edge, compresses into a thinner and more delicate line. The planet remains beautiful, but it also becomes more unified. Its many regions begin to present themselves as one globe rather than as separate places. Distance removes detail and increases wholeness. That visual change carries psychological weight. The crew is not merely farther from the launch site or from mission control, they are farther from the ordinary human frame of Earth itself, near the planet, even in orbit. There is a strong sense of attachment. The ground is always near. The horizon is broad and immediate. The world below is visibly active with storms, coastlines, deserts, and night lights. During the outbound coast, that intimacy declines. Earth becomes calmer to the eye, not because it is less alive, but because distance smooths its textures. The spacecraft cabin remains full of tasks, displays, and procedures. Yet through the windows, the most familiar object in human history begins to look more like a celestial body and less like an inhabited landscape. Operationally, this phase is also a transition from orbital routine to deep space routine. NASA's mission updates note that Orion has already transitioned to the Deep Space Network for communications after leaving Earth orbit, a step that reflects the growing scale of the journey. The Deep Space Network is the worldwide system of large antennas that supports missions far beyond low Earth orbit. In practical terms, that means the mission is no longer operating through the short-range habits of near-Earth flight. Communication remains steady, but the architecture behind it now belongs to interplanetary operations rather than orbital traffic. That shift is quiet, almost invisible from inside the cabin, yet it marks the moment when the mission begins to use the same broad communication framework that has long supported robotic voyages into the solar system. The outbound coast is not passive drifting. Small trajectory correction burns remain part of the flight plan, and NASA's current mission schedule describes 3 planned outbound correction opportunities to refine Orion's path as it travels away from Earth. These firings are much smaller than the departure burn that sends Orion onto the lunar path, but they matter precisely because long journeys magnify small errors. A slight deviation in pointing or velocity, if left untouched, can grow across the long distance into a larger targeting problem. The correction burns therefore show that leaving Earth's grasp is not a simple release. It is an actively managed departure, guided with care while the spacecraft continues outward through a widening region where direct recovery or quick return are no longer easy ideas. This widening region also changes the protective environment around the crew. NASA states that Artemis II carries its astronauts beyond Earth's protective magnetic field and into the deeper radiation environment of cislunar space. Near Earth, the magnetic field helps shield living things and spacecraft from some energetic charged particles. Farther out, that planetary protection weakens, and the mission must depend more directly on spacecraft design, monitoring, and solar weather forecasting. Orion carries radiation sensors in the cabin, and NASA and NOAA monitor the sun around the clock during the mission to watch for events that could raise radiation exposure. In this sense, leaving Earth's grasp is not only a matter of gravity and distance, it is also a matter of leaving behind part of the invisible shelter that Earth provides naturally. Inside Orion, the crew adapts to this new scale by settling into a rhythm that is calmer than ascent and more deliberate than early orbital checkout. NASA's recent flight updates describe the astronauts becoming acclimated to the space environment, beginning rest periods, exercising, and configuring the spacecraft for continued outbound flight. These ordinary acts matter because deep space travel is sustained not by spectacle, but by repetition, discipline, and comfort managed inside a very small volume. The outward journey is therefore lived in 2 dimensions at once. Outside, Earth shrinks and the void opens wider. Inside, the crew eats, rests, checks systems, and maintains the vessel that keeps distance survivable. So this 5th region of the journey is the long loosening of Earth's immediate hold. Gravity still reaches across the full span of space, and Earth remains the home world toward which every return calculation points. But visually, operationally, and physically, the spacecraft is no longer living in Earth's near neighborhood. The planet is now a retreating sphere. The communications network has shifted to deep space support. The protective magnetic environment has thinned away, and the mission settles into the measured outward rhythm of a crew truly leaving home. In this calm stretch after departure, the separation becomes real. Earth is still present in every thought, every system, and every glance through the window, yet it is no longer near. It has become a world seen across distance. There is no visible marker in space to show the farthest distance human beings have ever reached from Earth. No line hangs in darkness, no natural border changes colour, and no object waits to announce that one era has ended and another has begun. The record zone exists only as geometry, measurement, and history. It is a point along a trajectory where distance from Earth exceeds every earlier human voyage. That makes it a remarkable kind of place, because it is important without being tangible. Orion moves through the same black silence and the same broad field of stars as it does on the rest of the outward journey. Yet at one particular interval, the mission enters a region that carries a singular meaning in the record of exploration. NASA's current Artemis II mission planning places that threshold on Flight Day 6, when the crew is scheduled to pass beyond the Apollo 13 distance record, with Orion reaching its maximum distance from Earth later that same day. NASA also notes that the exact distance depends on launch day and time, because the Earth-Moon system does not repeat the same geometry perfectly from one departure to another. That dependence on geometry is part of what gives the record its quiet character. The farthest human travel is not simply a matter of deciding to go farther by force of will or by adding more speed. It emerges from the shape of the path, from the varying Earth-Moon distance, and from the exact way a spacecraft passes the Moon and falls back toward Earth. In this sense, the record zone is less like a summit and more like the outermost point of a curve drawn through moving gravitational relationships. The spacecraft does not stop there. It does not hover at the threshold. It passes through, and the record changes from future possibility to completed fact in an instant that navigation can define more precisely than the eye can perceive. For the crew, the transition would be known through mission data and mission time as much as through the view from the windows. Outside, Earth would already have become a small globe and the Moon would be growing in significance. Inside, the record itself would still arrive as a number. The previous holders of that number are the crew of Apollo 13. That mission is often remembered first for crisis, improvisation, and safe return. Yet it also holds the human distance record because of an unusual combination of circumstances. NASA's historical account explains that while Apollo 13 passed behind the Moon, James Lovell, Jack Swigert, and Fred Hayes became the most distant human travelers in history. The record arose because the Moon was farther out in its elliptical orbit than during other Apollo missions, and because Apollo 13's closest approach to the Moon was also farther from the surface than on the other lunar flights. The result was a maximum human distance of 248,655 miles from Earth, a record that has stood ever since. What matters here is that the old record was not created by triumphal intention alone. It emerged from a rescue trajectory and from orbital circumstance. The most distant human voyage was, in part, the product of survival. That history gives the record zone an unusual emotional tone. It is not merely a frontier left by bold expansion. It is also a remnant of vulnerability. Apollo 13 reaches its farthest point from Earth, while the mission is no longer aiming for a lunar landing and is instead working to bring the crew home alive. The outward edge of human travel is therefore linked, in memory, to a spacecraft in distress and to a crew moving through deep space under severe constraint. Artemis II approaches the same broad threshold under entirely different circumstances. It is a planned lunar flyby mission, not an emergency return, and its crossing of the record zone belongs to a deliberate test flight of Orion rather than to an accident. Yet the old history remains present in the meaning of the moment. To move beyond Apollo 13 is not only to go farther than before, it is to step beyond a line preserved for decades by one of the most fragile episodes in crewed spaceflight. In physical terms, the record zone also clarifies how large the Earth-Moon system truly is in human experience. Low Earth orbit feels remote from the ground, yet it is minuscule compared with the long outward arc required to pass the Apollo 13 record. By the time Orion reaches that threshold, the spacecraft is no longer in any ordinary sense near home. Communication still functions, navigation remains precise, the mission is still controlled and measured. But the scale has changed so much that Earth can no longer dominate the sky as a world of visible regions and familiar detail. It has become a distant whole. The distance record therefore works as a human scale marker. It translates celestial mechanics into lived separation. It says, in the simplest possible way, that no one has ever been this far from the home planet before, or that no one has been until this crossing occurs. The threshold also reveals how deeply human exploration depends on planning around changing celestial conditions. NASA's current Artemis II agenda states that the crew could set the record depending on the exact launch day and time. This does not weaken the significance of the milestone. It deepens it. The Earth and Moon are not fixed points on a diagram. Their separation changes as the Moon follows its elliptical orbit, and a crewed trajectory must fit into that moving architecture. The record is therefore not a static wall waiting in space. It is a moving consequence of where the Moon happens to be, how the spacecraft swings through the Earth-Moon system, and how the mission's free return path is shaped. Exploration at this scale is not only movement through distance, it is movement through timing. So this sixth region of the journey is a zone defined almost entirely by meaning. It is empty space transformed by memory, mathematics, and human continuity. Orion enters it without fanfare from the cosmos itself. No new landscape appears, no physical gate opens. Yet within the mission, the crossing marks a real expansion of the human record. The Apollo 13 line, held for more than half a century by a crew on a damaged spacecraft, becomes a point behind rather than ahead. Artemis II turns that long-standing outer limit into a passing place. For a few moments in the dark between Earth and Moon, distance itself becomes the subject, and human history grows slightly larger. Between Earth and Moon, the journey enters a region that is wide without visible structure. This is cislunar space, the broad corridor shaped by the gravitational relationship of the Earth-Moon system. It is not empty in the absolute sense, because light, particles, and gravity pass through it constantly. Yet to human perception it offers very little to hold on to. There are no continents, no cloud decks, no blue atmospheric edge, and no station lights repeating with each orbit. A crew crossing this region moves through a volume of space that has almost no local sign of passage. The spacecraft continues along a precise path, but the surrounding expanse gives no natural road and no horizon that can explain the motion at a glance. The route exists as mathematics expressed through movement, not as a visible track. This is one reason cislunar travel feels so different from ordinary orbital flight. Near Earth, the planet continually provides scale. Its curvature, colours, and repeated appearance make motion intuitively understandable. A spacecraft can be seen as circling something large and familiar. In cislunar space, that sense begins to dissolve. Earth is now behind or to one side as a distant globe. The moon is ahead as another body growing slowly in relevance. Between them lies an interval so broad that neither world fully dominates the visual field in the same way that Earth dominates low orbit. The crew travels through a middle region where the eye sees little change from moment to moment, even though the spacecraft is covering enormous distance. Hours pass, and the stars seem almost unchanged. Yet the spacecraft is moving through hundreds of thousands of kilometers of gravitationally structured space. The structure matters even when it cannot be seen. Earth remains the larger gravitational presence for much of the outward journey, but its pull weakens with distance. The moon's gravity grows more important as Orion advances. Cislunar space is therefore not a neutral gap between two separate destinations. It is a continuous field in which the influence of one world gradually gives way to the influence of another. The free return path used by Artemis II exists because these influences can be combined into a trajectory that bends naturally around the moon and comes back toward Earth. That means the broad expanse is not merely crossed, it is used. The spacecraft moves within the logic of the Earth-Moon system, taking advantage of how gravity shapes motion across large distances. To understand this region calmly, it helps to think of gravity not as a sudden pull from one side or the other, but as a changing landscape of motion. The spacecraft is always falling, yet never in the simple vertical sense familiar on Earth. It falls along a curve set by its speed and by the distribution of mass around it. In low Earth orbit, that fall is tightly wrapped around the planet. In cislunar space, the curve opens outward and the geometry becomes broader. The motion is still exact, but it is less visually obvious because there is no nearby surface to reveal the shape of the path. The crew may look out into darkness and feel stillness, while navigation shows a deeply structured trajectory unfolding with precision. This contrast between appearance and reality is one of the defining features of the cislunar corridor. The stars contribute to that impression of stillness. Unlike the ground beneath an aircraft or the clouds beneath a station window, the star field does not rush past. The stars are so distant that they remain effectively fixed over the course of the voyage. From 1 hour to the next, the great patterns of constellations barely change. This gives cislunar space a calm visual character, but it can also make the scale harder to feel. On Earth, speed is usually understood by seeing nearby objects move quickly. In deep space, there are no nearby objects. Motion must be known through instruments, through distance readouts, through mission time, and through the slow change in the relative sizes of Earth and Moon. The journey is therefore experienced partly through abstraction. Radiation and sunlight also shape the corridor, though less visibly than gravity. With Earth's magnetic shielding left behind, cislunar space exposes the mission more directly to the ambient environment of energetic particles and solar influence. Sunlight is strong and unfiltered by atmosphere. Shadow is sharp. Thermal conditions depend heavily on spacecraft orientation and surface properties rather than on any surrounding air. This does not make the region hostile in a dramatic way. It makes it exacting. Every exposed surface and every planned attitude must take account of a physical environment that offers no natural moderation. The broad corridor between Earth and Moon is quiet, but it is not gentle. Communication across this expanse adds another subtle sign of growing distance. Signals still move at the speed of light, and over the Earth-Moon span that means delay remains small by interplanetary standards. Yet it is no longer the near-instant closeness of low Earth orbit. More importantly, the psychological sense of support changes. The spacecraft remains in contact with Earth, but it is not surrounded by the infrastructure of near-Earth activity. There are no nearby stations, no frequent orbital traffic, and no immediate possibility of rapid rendezvous. Cislunar space feels sparse because it is sparse. This sparsity gives the region much of its meaning in human exploration. It is the first true outward corridor beyond the ordinary reach of crude spaceflight, a place where the home world and the destination world are both visible yet both distant in different ways. Earth is the place of origin, shrinking into a self-contained sphere. The moon is the approaching body, still not yet near enough to fill the sky or dominate the mission. Between them lies a volume that emphasizes relation over scenery. Cislunar space is important not because it contains striking landmarks, but because it reveals how travel between worlds actually happens. It happens through emptiness structured by gravity, measured by instruments, and understood through patience. So this seventh region of the journey is the long middle breadth of the Earth-Moon system, where silence, scale, and invisible structure become the main realities. The crew passes through a corridor that looks almost unchanged from moment to moment. Yet every hour carries them through a field of motion. There is no natural border announcing the center of the voyage. There is only the continued outward arc, the slow exchange of gravitational dominance, and the calm knowledge that human beings are moving through one of the widest and least familiar spaces they have ever entered. In deep space, Orion is not simply the name of a spacecraft. It is the entire artificial boundary between the crew and the surrounding vacuum. From the outside, it appears as a compact stack of joined elements moving quietly through darkness. But from the inside, it functions as a sealed working shell in which every ordinary human need has to be recreated by design. NASA describes Orion as the vehicle that carries and sustains the crew on Artemis missions, while ESA describes the European Service Module as the part that provides electricity, water, oxygen, nitrogen, temperature control, and propulsion. Together they form a small moving world, divided into a pressurized crew module where the astronauts live and an unpressurized service module behind it that keeps that life possible. In the broad corridor between Earth and Moon, this combined structure matters more than scenery or spectacle. The spacecraft becomes habitat, machine, shield, and workplace at the same time. The crew module is the human center of that world. NASA states that Orion's cabin has a habitable volume of 330 cubic feet, giving the crew living space roughly comparable to 2 minivans and noticeably more room than the Apollo command module once provided. Even so, the volume remains small for 4 people over many days. Seats, displays, controls, stowage, lighting, and the pathways of movement all have to serve several purposes at once. The commander and pilot sit where hand controls and displays are within immediate reach, while the mission specialists occupy the other side of the capsule. After launch, the foot pans for the forward seats can be removed and stowed, opening the central volume and making the cabin feel less fixed in its launch arrangement. In this region of the journey, Orion is therefore not spacious in the ordinary sense. It is efficient. It is shaped around reach, restraint, visibility, and the repeated conversion of one small interior from cockpit to living space, and back again as the mission requires. Behind that pressurized cabin, the service module acts as Orion's quiet provider. ESA describes it as an unpressurized cylindrical module about 4 meters long, carrying tanks, radiators, heat exchangers, and the systems that supply the crew with essential consumables. Once above the atmosphere, its solar arrays unfold until they span 19 meters, turning sunlight into electrical power for the spacecraft. Its propulsion system contains one main engine for large changes in velocity, 8 auxiliary engines for corrections and backup, and 24 smaller engines arranged in pods for orientation and fine control. In total, ESA describes the module as carrying 33 engines. This means the deep space shell is not a single sealed capsule carrying all functions inside itself. It is a partnership of volumes and roles. The crew lives in one section while another section, open to space and not meant for habitation, carries the resources and machinery that keep the inhabited part alive, pointed correctly, and able to move with precision. Orion in deep space is therefore less like a room with an engine, and more like a compact organism whose life depends on cooperation between different attached bodies. Inside the inhabited volume, survival depends most directly on the environmental control and life support system. NASA explains that this system must make the crew module habitable and safe on deep space missions, where rapid return is not possible. Air has to be refreshed, pressure has to remain stable, humidity has to be controlled, and trace contaminants produced by human presence have to be prevented from building up. Orion uses a regeneral system that removes carbon dioxide and humidity from the cabin air, then vents them overboard into space during regeneration, saving mass and volume compared with older expendable methods. High-pressure oxygen and nitrogen tanks support cabin pressure control, while environmental monitoring watches temperature, pressure, and humidity and detects unsafe changes in the enclosed atmosphere. Water is stored and distributed for drinking, food preparation, medical use, and hygiene. These facts make Orion's deep space shell different from the popular image of a capsule as a rigid protective can. Its deeper reality is metabolic. Air cycles, heat moves, water is rationed and dispensed, and the cabin remains safe only because the spacecraft continuously maintains an artificial internal environment against a naturally lethal external one. That same shell also has to support the crew as human beings rather than merely as passengers with oxygen. NASA's Artemis II crew systems material describes Orion as carrying a water dispenser, a food warmer, a flywheel exercise device, a medical kit, sleep arrangements, and the universal waste management system. The astronauts are scheduled to exercise each day to reduce the physical losses that accompany weightlessness, using a compact flywheel device small enough to fit Orion's mass and volume limits. They sleep attached to the walls in sleeping bags, with full rest periods deliberately built into the mission timeline. Hygiene is handled with stored supplies, liquid soap, rinseless cleaning methods, and a compact hygiene bay that includes privacy doors and the spacecraft toilet. Should minor medical needs arise, a medical kit and diagnostic tools can support consultation with flight surgeons on the ground. These details may appear ordinary, but in deep space their ordinariness is precisely the achievement. Orion's cabin is designed to make eating, sleeping, exercise, waste handling, and basic medical care possible in a volume too small to waste, too distant for rescue, and too important to allow bodily needs to become operational failures. The shell must also remain protective when the cabin itself is threatened. NASA states that Orion's crew survival system suits are used on launch day, in emergency situations, during high-risk parts of missions near the Moon, and during the high-speed return to Earth. The agency also notes that Orion's closed-loop life support capability can maintain a positive pressure, breathable atmosphere, and thermal cooling to suited crew members for up to 144 hours in the event of a pressure vessel leak or contaminated cabin atmosphere. This means Orion is built with layers of habitability. The nominal layer is the cabin itself, where the crew works freely in shirt sleeves. The contingency layer is the suited crew, still protected even if the cabin can no longer serve as a safe common atmosphere. In deep space, that distinction matters. A spacecraft far from Earth cannot depend on outside help arriving quickly. It must carry its own fallback conditions within the same narrow shell. Orion therefore presents itself in this region of the mission as a deliberately compact refuge, one whose value lies not in comfort alone but in resilience. It holds 4 people inside a volume that's always small, often busy, and never naturally safe. Yet it turns that volume into a place where work, rest, and survival can continue together, while the vast emptiness outside remains untouched by human need. Far from Earth, the mission is sustained less by spectacle than by rhythm. Distance alone does not carry a crew safely through deep space. What does so, hour after hour, is the steady repetition of ordinary acts performed within a highly unusual environment. Inside Orion, the astronauts do not live in a state of constant drama. They wake, eat, exercise, inspect equipment, answer scheduled tasks, clean their small surroundings, record observations, and prepare for sleep. The farther the spacecraft travels from Earth, the more important this rhythm becomes, because routine is one of the main forms of stability available in a place where gravity, weather, daylight, and ordinary human surroundings no longer provide their familiar structure. In that sense, the crew's daily pattern is not separate from mission success. It is one of the conditions that make success possible. Time in the spacecraft is carefully arranged. Sleep is not treated as leftover time after the work is done. It is part of the work of keeping the crew capable. NASA's Artemis II planning describes a full sleep period built into the mission schedule, with all 4 astronauts sleeping at the same time for much of the flight. That shared rest period matters because it gives the spacecraft a common daily shape. The cabin can become quieter. Lighting can be adjusted to support rest. Non-essential activity can pause. Each astronaut secures a sleeping bag to the interior wall, turning the surfaces of the cabin into temporary sleeping space. In weightlessness, there is no mattress in the ordinary sense and no up or down to determine a bed. Sleep is therefore an act of restraint and adaptation. The body is gently held in place. The cabin becomes dimmer, and the crew rests inside a volume that remains small, enclosed, and always softly mechanical in its background sounds. Even in deep space, the body still requires a cycle of waking and sleep, and the spacecraft has to make that cycle possible. When the crew wakes, the day begins not with walking across a room or stepping into a corridor, but with orienting the body in microgravity and re-entering a shared workspace that has been a sleeping area only moments before. This is part of the distinct rhythm of life aboard Orion. The same compact volume must support several modes of living without wasted space. Bags are stowed, restraints are adjusted, and the cabin returns to work configuration. Meals become part of that transition. Orion carries water and food systems designed for short deep space missions, and eating is handled with the calm efficiency required by limited volume and careful storage. Food must be prepared, opened, warmed when needed, and managed so that crumbs, droplets, and packaging do not drift into equipment or ventilation paths. Even eating, which on Earth can be casual and spread across a room, becomes an act of order. It is nourishment, but it is also housekeeping. Exercise enters the day for a similar reason. In weightlessness, the body begins to lose the ordinary loading that gravity gives to muscles and bones. Orion's crew system therefore includes a compact flywheel exercise device that allows both resistance work and aerobic effort. The astronauts use it as part of their daily routine, not because deep space invites athletic performance, but because the body has to be reminded that it is still expected to remain strong. Exercise in Orion is also different from exercise on Earth, because it takes place in a very confined environment. The crew must work around one another, around equipment, around schedule, and around the reality that movement in microgravity transfers force into the cabin structure unless it is carefully managed. Yet this daily effort serves more than physiology. It also creates continuity. Repeated physical exertion helps shape time, breaks the day into human segments, and gives the crew a familiar form of effort in a place where ordinary bodily experience has been altered. Much of the routine is quieter than exercise and less visible than navigation or system checks. The crew monitors the cabin, reviews procedures, answers planned tasks, and works through checklists that keep the spacecraft healthy while also keeping themselves oriented. A spacecraft far from Earth cannot be allowed to become cluttered, uncertain, or loosely organized. Small objects must be restrained. Tools must return to their places. Waste must be handled correctly. Surfaces may need wiping. Equipment must be checked not only when something seems wrong, but when everything appears normal, because consistency is part of safety. This makes the daily rhythm of the crew both human and procedural. It includes moments of ordinary living, but those moments are always nested within a structure of observation and care. Privacy becomes a subtle part of that structure. Orion is designed for a crew rather than for solitary travel, yet its habitable volume remains small. That means privacy cannot depend on physical distance. It depends instead on habits of respect, careful scheduling, and the brief use of enclosed spaces when available, especially for hygiene and waste handling. NASA's descriptions of life aboard Orion emphasize that even these basic personal needs are planned in detail. The spacecraft carries a hygiene bay and a waste management system designed for multi-day flight in zero gravity. In the broader view of space exploration, such systems may seem less dramatic than propulsion or navigation, but in daily life they are essential. A mission can only remain calm and workable if bodily needs are handled cleanly, privately, and reliably. Communication with Earth also becomes part of the crew's rhythm, though not always in a dramatic or ceremonial sense. Messages, conferences, and scheduled exchanges with the ground help organize the day and preserve a living connection to home. Yet these conversations are folded into routine rather than standing outside it. They belong to the pattern of work, health, and mission awareness. Far from Earth, communication is not simply emotional reassurance. It is also part of maintaining shared understanding between the crew and the teams supporting them from the ground. So this ninth region of the journey is made not of scenery but of repetition. The astronauts live within a narrow shell moving through a vast and silent corridor, and they remain effective by building a day out of sleep, meals, exercise, hygiene, procedure, and shared discipline. Deep space travel, at the human level, is not sustained by intensity alone. It is sustained by rhythm that returns each day and makes the extraordinary gradually livable. As Orion approaches the Moon, the journey enters a new visual order. For much of the outward passage, Earth has remained the stronger emotional reference even while growing smaller, because it is the home world and because human attention naturally follows what is being left behind. Near the Moon, that balance begins to shift. The lunar disk, which had been a distant object ahead, grows steadily larger and more detailed, is easier to understand by sight. The Moon no longer appears as a destination marked only on screens and trajectory plots. It becomes a nearby world with visible structure, clear curvature, and a surface that can be studied directly through the windows. In this phase, The mission is still in approach rather than passage. Orion has not yet rounded the moon. It is still closing the distance, and the growing presence of the lunar body begins to organize the meaning of the flight. The first change is one of scale. Unlike Earth, the moon has no thick atmosphere to soften its edge or blur its limb with color. It presents a sharp outline against black space. As Orion comes nearer, the disk expands with unusual clarity. Bright highlands and darker maria, the broad basalt plains formed long ago by ancient volcanic flooding, become easier to distinguish. Crater rims catch sunlight in hard contrast. Shadowed interiors appear black and abrupt. The entire world looks dry, fixed, and old. From Earth, the moon is familiar almost to the point of seeming simple. From approach distance, that familiarity gives way to a more exact impression. The surface is not smooth. It is heavily written with impacts, basins, ridges, and overlapping structures that reflect billions of years of exposure. The astronauts do not yet skim close over it as Apollo crews once did in lunar orbit. Artemis II approaches at a much higher altitude, which means the moon remains whole in the field of view for longer. NASA's current mission visuals describe this perspective as one that allows the crew to see the full lunar disk, including regions near both poles, from a distance of several thousand miles above the surface at closest approach. That makes the approach visually broad rather than locally detailed. The moon grows large without yet dissolving into a rushing landscape. This broadness gives the approach a distinct calm. In low lunar orbit, a crew would see the surface slide rapidly beneath the spacecraft, and individual topography would dominate attention. On Artemis II, the approach holds the moon at a scale that is planetary rather than purely local. The crew sees not only surface markings but also the shape of the world as a whole. The poles remain part of the visible disk. The great curve of the limb stays clear. The contrast between illuminated terrain and darkness emphasizes the moon as a body in sunlight rather than merely as ground. This matters because the mission is not designed to enter orbit and remain near the moon. It is designed to approach on a free return path that uses the moon's gravity, while still preserving the visual and geometric sense of a flyby world. The approach, therefore, has a surveying quality. Orion closes in on the moon not as a station arrives at a planet-sized object through repeated orbits, but as a traveller approaches a single great turning point in space. Navigation becomes more intuitive here, though no less exact. During the long cislunar crossing, movement is primarily understood through instruments, timing, and the slow changes in the relative size of Earth and Moon. Near approach, the Moon itself begins to explain the motion. Its apparent size increases. Its position relative to the spacecraft windows shifts in a way that can be felt by the eye, as well as calculated by software. Yet the path is still governed by precision rather than by visual aiming. Orion is not steering toward a landing site or targeting a low circular orbit. It is arriving on a carefully chosen geometry in which altitude, lighting, timing, and gravitational relation all matter together. Small correction burns made earlier in the outbound flight help ensure that this closing angle remains correct. The approach is therefore the visible result of many earlier decisions. What the crew now sees growing outside the windows has already been shaped by quiet course management over days of travel. The moon also changes the light inside the journey. Its brightness is different from Earth's. Earth appears alive with cloud reflection, atmospheric glow, and changing weather. The moon reflects sunlight more starkly, with fewer soft transitions. The terminator, the line between lunar day and lunar night, can appear especially dramatic because it cuts across a surface rich in relief. Mountains and crater walls stand out where sunlight arrives at a low angle. Shadow reveals depth directly. This sharpness helps the surface read as solid and ancient. It also reminds the crew that the moon is not merely a symbol of exploration, but a physical world with its own geology, temperature extremes, and long exposure to impact. On approach, the astronauts are still outside that world and still separated from it by thousands of miles, yet it now occupies the mission's visual foreground. Earth remains present during this phase, though in a changed role. NASA's Artemis II material notes that from the crew's far vantage, they will be able to see the moon near in the foreground and Earth far behind it. That arrangement changes the emotional center of the view. Earth is still the home planet, but it is no longer the large surrounding reality. It becomes the distant companion in the scene, smaller and softer than before, framed by the nearness of another world. This pairing gives the approach much of its human meaning. Few people have ever seen Earth and Moon arranged in this way from a crewed spacecraft, with one world nearby and the other set deep in the background across nearly 250,000 miles of space. So this 10th region of the journey is the slow transfer of visual authority from Earth to Moon. The outward corridor narrows into a meaningful encounter. The moon grows from target to presence, from known symbol to detailed world, and the spacecraft closes toward it under exact guidance. Approach does not yet complete the turn around the moon. It prepares it. In this interval, the crew sees the lunar body become real at close range, large enough to dominate the windows, distant enough to remain whole, and clear enough to show why the old familiar face of the moon is in fact the surface of a fully formed world. The lunar flyby is the moment when approach becomes passage. Orion no longer sees the moon chiefly as a growing world ahead. It begins to move around it, and the geometry of the mission changes from closing distance to bending motion. This is not lunar orbit. The spacecraft does not settle into repeated revolutions around the moon. Instead, it follows a single free return curve that carries it behind the moon and then guides it back outward on a path that will lead again toward Earth. In this brief but consequential region, the moon becomes both nearby world and gravitational turning body. Orion passes it at a much higher altitude than the Apollo crews used when they entered lunar orbit, remaining several thousand miles above the surface. That higher path preserves the broad planetary view while still bringing the spacecraft close enough for the moon's gravity to shape the journey in a decisive way. As the flyby begins, the visible relation between spacecraft and moon changes steadily. On approach, the lunar disk remains largely in front of the crew, growing and shifting only gradually. During the flyby, the world begins to slide across the windows with a stronger sense of motion. Features that were once presented as part of a nearly full disk now shift toward the limb. The curve of the moon becomes more dominant than its face. The spacecraft is no longer simply looking at the moon. It is passing it. This gives the flyby a distinct visual character. The moon does not rush past in the way a low orbiting landscape would, yet it no longer feels fixed ahead either. It becomes a body being rounded, a massive sphere whose presence changes the direction of the voyage. The far side gives this passage much of its identity. From Earth, only one lunar hemisphere is seen easily with ordinary observation, because the moon rotates in such a way that nearly the same face is turned toward Earth over time. The far side is therefore not mysterious in the scientific sense, since orbiters and earlier crews have photographed and studied it, but it remains unusual in human experience. Very few people have ever seen it directly with their own eyes from nearby space. As Orion moves around the moon, the Earth-facing side gives way to regions never visible from the ground. The surface there has a different visual balance from the near side. It contains many craters and relatively fewer of the large dark maria that make the near side so recognizable from Earth. The far side appears older in expression, heavily marked, bright in tone, and densely textured with impact history. From the Artemis II flyby altitude, the crew would still see it as part of a large whole rather than as a swiftly passing local terrain, but the distinction between the familiar hemisphere and the hidden one would remain clear. At the same time, Earth changes position in the sky of experience. Near the deepest part of the flyby, Orion reaches the interval of greatest separation from home. NASA's current mission descriptions note that the exact maximum distance depends on launch timing and the Earth-Moon geometry, but the farthest point is expected to occur around the time of the lunar pass. This means the Moon is not only the nearby body then, it is also the pivot around which human distance from Earth reaches its outermost extent. The flyby therefore joins two meanings in one place. It is the closest encounter with the Moon of the mission, and it is the farthest removal from Earth. These two conditions meet because the spacecraft is not going to the Moon in a straight line and stopping there. It is curving through a gravitational relationship that stretches human travel outward to its widest point, just as the Moon's presence becomes most immediate. Communication also takes on a special character here. As Orion passes behind the Moon, the direct line between spacecraft and Earth is interrupted. The Moon itself blocks the signal. This blackout is temporary and expected. It is not a crisis, but a natural consequence of geometry. Yet it carries a quiet significance, because it produces an interval in which the crew is not in live contact with the home world. For a short span, the spacecraft moves through the far side region with the Moon physically between Orion and Earth. In operational terms, this is planned and understood. In human terms, it is a rare form of separation. The crew is not only far from Earth, it is briefly hidden from it by another world. The free return nature of the flyby means that gravity does the deepest work without spectacle. There is no need for a large engine burn to send Orion back toward Earth at this moment. Instead, the spacecraft passes through the Moon's gravitational field along a chosen path that bends the outbound trajectory into an inward one. This is one of the most elegant aspects of the mission. The Moon is not merely a destination being observed from near at hand. It is the body that turns the spacecraft home. The curvature of the path is therefore not incidental to the scenery. It is the physical purpose of the flyby. Orion arrives with one direction of travel and leaves with another, not because the spacecraft stops and starts anew, but because the geometry of motion through the Earth-Moon system allows the journey to fold around the Moon and continue. From inside the cabin, the farside flyby would likely feel both calm and concentrated. The crew would remain occupied with observation, procedures, and the discipline of a timed mission event. Yet the visual scene would be unlike any ordinary orbital operation. The Moon would fill a substantial part of the windows, not as a symbol, but as a real nearby sphere. The hidden hemisphere would pass into view. Earth would be absent or displaced. Distance from home would reach its maximum. Then, gradually, the logic of the scene would begin to reverse. The Moon would no longer be something being approached from afar. It would become something already past, still nearby for a time but no longer ahead. So this 11th region of the journey is the Great Turn itself. Orion passes around the far side of the Moon at a high flyby altitude, sees the hidden hemisphere directly, enters the interval of greatest human distance from Earth, and lets lunar gravity redirect the mission onto its return path. It is the closest and farthest moment at once, nearest to another world and most removed from the home one. In the calm precision of that turning passage, the moon ceases to be only a destination and becomes the agent that bends human travel back toward Earth. Once Orion has passed the far side of the moon, the journey does not simply reverse in a visual or mechanical sense. The spacecraft is not turning around like an aircraft making a wide arc in the sky. It is continuing forward along a new curve, one reshaped by the moon's gravity. This is the essence of the free return path. NASA describes Artemis II as flying a free return trajectory that swings around the far side of the moon and then brings Orion back toward Earth, with the translunar injection burn having already set that return in motion days earlier. In this arrangement, the moon functions less as a stopping place than as a turning body. Orion arrives from Earth on one broad arc, passes the moon at high altitude, and leaves on another broad arc whose direction now leads home. The return has therefore already begun by the time the flyby is complete, even though the spacecraft has not used a new major engine burn to start it. The path itself contains the return within it. That feature gives the mission a particular elegance. In ordinary language, a return trip often suggests a separate decision and a separate act of propulsion, as though one journey ends and another begins. The free return path does not work that way. It links the outward leg and the inward leg into one continuous gravitational design. NASA's press kit notes that Orion's translunar injection burn is the last major engine firing of the mission, and that it places the spacecraft on the free return trajectory that will ultimately bring the crew back to Earth for splashdown. Another NASA mission description adds that the spacecraft uses the moon's gravity to send Orion back to Earth without additional major propulsive maneuvers. The mission does not spend large propulsion at the moon in order to force a homeward turn. It relies instead on timing, geometry, and the gravitational shape of the Earth-Moon system to make the homeward curve a natural continuation of the flight. The word free and free return can sound simple, but the path is not effortless and it is not casual. It is free only in the sense that, once the spacecraft has been inserted onto the proper lunar trajectory, the large-scale return does not require another major burn to begin. Everything about that outcome depends on exact preparation. NASA's current trajectory materials show that Orion's course is chosen, so the moon's gravity bends the spacecraft onto a return to Earth, while smaller outbound and return correction burns remain available as needed to keep the aim precise. The freedom, then, is freedom from large additional propulsion at the turning point, not freedom from navigation or correction. Orion still travels through a field of exact relationships. Its speed, angle of passage, altitude at flyby, and relative position to Earth and Moon all matter. The free return path succeeds because the spacecraft enters that geometry correctly and remains close enough to the intended line that small correction burns can preserve it. This makes the region after the flyby unusual in its emotional character. During approach, the moon grows and the spacecraft seems drawn outward toward another world. During the free return passage, the moon has already done its turning work. Even though it may still remain large in the windows for some time, the motion now belongs to Earth again, but not because Earth has suddenly grown visually dominant. Instead, the mission's hidden logic has shifted. The spacecraft is being carried away from the moon on a curve whose destination is once more the home planet. The eye may still be impressed by lunar closeness, but the mathematics of the mission has changed. Earth is again the world that defines the future of the path. The free return trajectory also reveals something important about deep space mission design. In crewed exploration, safety is not a separate layer added after performance has been achieved. It is built into the architecture of the mission itself. A free return path offers resilience because the broad return does not depend on executing a large main engine burn at the moon in order to get home. By contrast, Artemis II's path is selected so that the translunar injection burn has already committed Orion not only to reaching the Moon, but also to coming back from it. NASA has even described that burn as effectively doubling as Orion's deorbit burn, because once it is completed successfully, the mission is set on a path that leads all the way to Earth re-entry. In this sense, the free return path is not merely efficient, it is prudent. There is also a deeper physical calm to this arrangement. The spacecraft does not fight the Earth-Moon system, it moves within it. The Moon is used as a gravitational partner that redirects the spacecraft, while preserving the overall shape of the mission. This is why the path feels less like a sharp turn than like a great sweep. Orion does not stop at the Moon and then start again. It passes through a changing gravitational landscape, and that landscape carries the spacecraft from one branch of the mission to the other. What the crew experiences as continued motion through darkness is, at a deeper level, a transition from outbound to inbound geometry, accomplished by the natural structure of the system. NASA's current Artemis II timeline places the trans-Earth return phase immediately after the lunar flyby, with return trajectory correction burns available as necessary to aim for Earth's atmosphere. That phrasing is revealing. The large shape of the return already exists as soon as the Moon has bent the spacecraft's path. The remaining burns are not the source of the homeward route. They are refinements of it. Orion has already been handed back to Earth by the combined geometry of the mission and the Moon's gravity. So this 12th region of the journey is the great folded arc after the turn, the part of the mission in which the return is present not as a decision newly made, but as a condition already built into motion. Orion continues onward after passing the Moon, yet onward now means inward toward Earth. The free return path joins distance and restraint, showing that the farthest human voyage is also carefully designed to be a voyage that comes back. In the quiet after the flyby, the Moon falls gradually behind. The homeward curve has already been accepted by the spacecraft, and the journey reveals one of its most graceful truths that in deep space, the safest path can also be the one most completely shaped in advance by gravity itself. After the Moon has bent Orion onto its homeward path, the return through cislunar space begins as a long inward coast rather than a dramatic reversal. The spacecraft does not seem to turn around in any ordinary visual sense. It continues forward through darkness. But the meaning of forward has changed. The journey is no longer a movement away from Earth into increasing distance. It is now a movement toward Earth through steadily closing separation. NASA's current Artemis II mission design describes the return trip from the Moon as taking about 4 days, with the spacecraft following the free return path set earlier in the mission and using smaller return trajectory correction burns as needed to stay aimed correctly for home. In this region, the broad architecture of the voyage has already been decided. The Moon has done its turning work, and Orion now spends several days crossing the same wide Earth-Moon corridor in a different psychological direction. The crew is still far from Earth, still inside the same compact shell, and still moving through the same sparse expanse. Yet the underlying sense of the flight changes almost at once. Distance is no longer something still being gained. It is something being slowly given back. The visual order of the journey also begins to reverse. During the outward coast, Earth slowly shrinks and the Moon grows from a distant target into a nearby world. On the return, the Moon begins to recede and Earth gradually resumes authority in the windows. At first the change is subtle. The Moon remains a substantial presence for a time after the flyby, still close enough to dominate attention and to remind the crew that they have only just passed another world. But as the hours continue, the lunar disk diminishes and the home planet begins its slow enlargement. Earth does not expand suddenly. It gathers presence little by little, first as a small globe, then as a clearer sphere with more legible cloud structure and brighter contrast between ocean, land, and atmosphere. That quiet visual growth matters because it restores an old human reference. The crew is still in deep space, but the home world is becoming more like a destination than a memory. The journey inward therefore feels less like entering a new region than like gradually re-establishing connection with a world already known. The farther the return progresses, the more Earth ceases to be the distant background of the scene and becomes once again the object around which all timing, preparation, and attention are organized. Operationally, the return through cislunar space is quieter than the lunar flyby, but not passive. NASA's current daily agenda for Artemis II shows that the inward leg includes return trajectory, correction opportunities, allowing controllers and crew to refine the path as Orion comes back toward Earth. These are small burns compared with the earlier departure burn from Earth orbit, yet they remain essential because the spacecraft is still crossing a very large volume of space. Over such distances, even a minor difference in velocity or pointing can widen into a larger targeting error if left untouched. The return corrections, therefore, do not create the homeward path, they preserve it. This distinction is important. The free return geometry gives Orion its large inward curve, but careful navigation keeps that curve precise enough to deliver the spacecraft where it needs to be at the end of the crossing. During this phase, the spacecraft also continues the ordinary disciplines of deep space flight. Systems are monitored, consumables are tracked, and the crew maintains the cabin in a condition that supports both daily life and later mission events. NASA's mission schedule for the later flight days describes the astronauts exercising, conducting biomedical activities, returning the cabin toward its original configuration, and preparing equipment for the final stages of the flight. All of this belongs to the inward crossing itself. The return through cislunar space is therefore not a mere wait for Earth to grow larger. It is an active interval of aiming, housekeeping, and controlled transition from the broad freedom of deep space travel toward the tighter demands of arrival. This inward passage also changes the emotional geometry of the mission. On the outward leg, much of the psychological force comes from leaving. Earth shrinks, protection thins, and the crew travels toward a distance that few human beings have known. On the return, the force comes from approach. Earth is still far away, but it is no longer receding. That alters how time is felt. Each completed day now has a reducing quality rather than an extending one. The spacecraft remains isolated. Communication still depends on long-range support, and the surrounding void remains as empty as before. Yet the mission's horizon has changed. Home is now somewhere ahead along the line of motion rather than somewhere behind across a widening gap. This does not make the return easy or ordinary. Orion is still beyond the region of quick rescue and still dependent on its own systems for every human need. But the direction of risk and purpose is different. The spacecraft is carrying its crew not into deeper unfamiliarity, but back toward the planetary environment from which the mission began. In that sense, the return through cislunar space has a steadier emotional texture than the outward coast. It is not defined by anticipation of first encounter, it is defined by gradual reconnection. So this 13th region of the journey is the long closing corridor between the moon already passed and the Earth not yet reached. Orion crosses it under the logic of a path already shaped by gravity, with small corrections preserving its aim and daily routines preserving the crew's readiness. The moon falls back into distance. Earth grows slowly from a remote globe into a clearer destination. Inside the cabin, The mission becomes one of preparation and maintenance as much as motion. Outside the windows, the broad emptiness of cislunar space remains unchanged, yet its meaning is no longer the meaning of departure. It has become the final great interval of return, the calm inward stretch in which human beings carry deep space experience back across the Earth-Moon system toward the world that first sent them out. On the final day of the mission, Orion comes back not by gently descending through calm air, but by meeting Earth at lunar return speed. This is the most thermally severe phase of the flight, and it is one of the main reasons the mission exists as a test of a deep space crew vehicle rather than as a simple voyage around the Moon. By the time the spacecraft nears Earth, the broad cislunar crossing has ended, and the destination is no longer an expanding globe in the windows alone. It becomes an atmosphere, an ocean, and a carefully chosen recovery region in the Pacific. Before Orion enters that atmosphere, the spacecraft must change form for return. The crew module, the pressurized capsule that carries the astronauts, separates from the service module that has supplied propulsion, power, and consumables through the mission. The service module does not survive the return. It falls away and burns up during atmospheric entry, while the crew module continues alone. At that moment, Orion becomes a smaller, simpler shape, stripped down to the part designed to endure the descent and protect the people inside. The crew module must then hold the correct orientation. Its heat shield faces into the flow, because the purpose of the capsule during entry is not to cut cleanly through the atmosphere like an aircraft. It is to use drag and controlled lift to shed enormous speed while keeping the hot external environment away from the cabin. Orion returns from the Moon at more than 25,000 miles per hour, far faster than spacecraft returning from low Earth orbit. That difference matters because heating rises sharply with speed. The atmosphere that seemed absent and remote during launch now becomes the decisive medium of survival. Friction is not the full explanation in a simple everyday sense. The real process involves the violent compression and heating of air around the spacecraft as it rushes through the upper atmosphere. The heat shield absorbs and sheds that energy through ablation, meaning its outer material chars and erodes in a controlled way so that heat does not pass inward in dangerous amounts. The shield is therefore not merely a hard shell. It is a sacrificial thermal system, designed to be consumed in part so the crew can remain safe behind it. Orion's return profile is also unusual because it uses what NASA calls skip entry. In this technique, the capsule first dips into the upper atmosphere and slows, then lifts back out before entering again for final descent. The purpose is not theatrical complexity, it is control. The skip gives Orion greater range and more flexibility in reaching a planned landing area in the Pacific, while also managing the entry environment in a way suited to lunar return. This means the spacecraft does not simply plunge once and continue downward without interruption. It interacts with the atmosphere in stages, using shape, lift, and guidance to stretch and refine the path toward splashdown. For the crew, this is a physically demanding interval. After days of weightlessness, the body feels acceleration return. The capsule is enclosed in plasma. Communications can be interrupted during blackout, and the view outside shifts from black space to the bright and violent invisibility of superheated entry conditions. As Orion descends deeper and speed falls, the return changes character again. What begins as thermal survival becomes controlled deceleration under parachutes. Near the end of the high-speed phase, the forward bay cover is jettisoned from the top of the capsule, exposing the parachute system. Orion carries 11 parachutes in all, arranged in a sequence that turns a falling deep space capsule into a slow, water-landing vehicle. Small parachutes first pull away the cover. Drogue parachutes then slow and stabilize the crew module. Pilot parachutes draw out the main parachutes, and the 3 large mains finally open to bring the descent rate down to a level suitable for astronaut safety at splashdown. The effect is a steady conversion of violence into manageability. The capsule that had been enduring one of the harshest heating environments in human flight is now hanging beneath fabric canopies above the ocean, descending toward water instead of rock or runway. The landing itself is a splashdown in the Pacific Ocean, with current Artemis II planning placing the return west of Baja California. Water recovery is not an afterthought from an older era. It remains the chosen method because Orion is a large deep space capsule returning at lunar velocity, and the Pacific offers the broad recovery region needed for the mission's entry geometry. Splashdown ends the flight in one sense, but it does not end the operation. Once the capsule hits the water, the mission changes again from spacecraft return to crew recovery. NASA and Department of Defense teams position ships, boats, helicopters, divers, medical personnel, and imaging assets in advance, because Orion may land far from shore and the crew has to be reached quickly. On recovery day, the teams begin preparations hours before entry. Helicopters are airborne before splashdown. Small boats and the recovery ship hold at a waiting position until Orion has passed through blackout and is close enough to track precisely. After splashdown, there are a brief pause to allow falling debris to clear the area. Then the recovery force moves in. The first priority is the crew, not the capsule. Boats approach and hold near Orion while post-landing checks are completed and authorities transferred from mission control to the recovery director. The hatch is opened only after the capsule is safe and the sequence is ready. A medical officer is the first person to go inside, assessing the astronauts after their long return from deep space and their abrupt reintroduction to gravity. Outside the hatch, divers and recovery personnel prepare a temporary platform known as the front porch. One by one, the astronauts are helped out of the capsule onto that floating platform and fitted with recovery vests. Helicopters then hoist them from open water and carry them to the recovery ship, where medical assessment continues. NASA's current recovery planning aims to have the crew back aboard ship within about 2 hours of splashdown. Only after the astronauts are safely away does the spacecraft itself become the focus. Recovery teams reconfigure the cabin, close the hatch, and prepare the capsule to be taken aboard ship. Orion is too large and heavy to be lifted in the old fashion used for some earlier capsules, so it is floated and winched into the well deck of the recovery vessel. Once the capsule is secured and the deck is drained, Orion is finally hard down, stable and contained. The mission has come all the way from launch pad to lunar distance, from deep vacuum to ocean water, and the spacecraft ends its return enclosed inside a ship rather than flying through space. In this final operational region, re-entry and recovery reveal their quiet logic. The atmosphere slows what space had accelerated. The ocean receives what the heat shield preserves. The recovery team turns a floating capsule back into a human landing. By the time Artemis II nears the close of its mission, the farther frontier has changed meaning. At the beginning of the voyage, distance is the most obvious measure. The crew leaves Earth, passes beyond the old Apollo record zone, rounds the moon, and returns across cislunar space. Yet the deeper meaning of the mission does not rest in mileage alone. NASA describes Artemis II as the first crewed Artemis flight, the first mission with astronauts aboard SLS and Orion, and a key step toward the long-term return to the Moon and later missions toward Mars. That language matters because it places the mission in a larger sequence. Artemis II is not designed as an isolated expedition whose value ends when the crew splashes down. It is designed as a proving passage, one that carries human beings far from Earth in order to test whether the systems, habits, and operations needed for sustained deep space exploration can hold together under real conditions. In that sense, the farther frontier is not only a physical edge between Earth and Moon, it is the boundary between demonstration and repetition. Before Artemis II, the outward human journey to lunar distance belongs mostly to memory and history. After Artemis II, it becomes a present capability again. That change is important because deep space exploration depends on continuity more than on a single dramatic crossing. Apollo proved that human beings can reach lunar distance, orbit the Moon, land on its surface, and return. But Apollo also ended, and for more than half a century no crew travelled beyond low Earth orbit. Artemis II therefore restores something that had lapsed. NASA's current program descriptions present it as a mission that builds on the uncrewed Artemis I flight and demonstrates a broad range of capabilities needed for missions farther from Earth. The spacecraft must support people, not only sensors. The life support systems must function with a crew aboard in deep space. The vehicle must show that communication, power, guidance, habitability, radiation procedures, and operational discipline can work together across the full span of a lunar flyby mission. This makes Artemis II a threshold between testing hardware and testing a human exploration system. A rocket can fly once and prove performance. A capsule can survive once and prove design. But a human deep space capability is only truly established when people live inside it, trust it, and bring it home through the full chain of mission events. Artemis II occupies that exact place in the order of things. It is the mission where the architecture becomes inhabited. The farther frontier also changes because Artemis II is outward-looking without being a landing mission. Its purpose is not to place astronauts on the lunar surface. That belongs to later flights. NASA's official Artemis descriptions say Artemis II paves the way for future lunar surface missions, and NASA's long-range program framing presents Artemis as part of a return to the Moon intended to build experience and infrastructure relevant to Mars. This means the value of Artemis II lies partly in what it does not attempt. By choosing a crewed lunar flyby rather than an immediate landing, the program places emphasis on sequence, on learning, and on reducing uncertainty one layer at a time. The mission takes the human crew through launch, Earth orbit checkout, translunar injection, deep space operations, lunar flyby, free return navigation, atmospheric entry, and recovery. Each of these phases is a necessary piece of later exploration. Together they form a bridge between an uncrewed pathfinder and later surface expeditions. The farther frontier, therefore, becomes procedural as much as geographic. It is the point at which the mission chain grows long enough and complete enough to support the next step. Artemis II does not stand at the end of a road. It stands where the road becomes dependable enough to carry more ambitious journeys. There is also a quieter human meaning to this frontier. Artemis II carries a crew into a region no humans have visited in more than 50 years, and in doing so it changes what counts as recent human experience. Before this mission, living memory of deep space flight belongs to a shrinking group of Apollo veterans and to the historical record they leave behind. After this mission, deep space travel is no longer something known only through archives, museum hardware, and remembered voices. It becomes something newly lived by a new crew under modern conditions. NASA's own descriptions emphasize that Artemis II will carry astronauts farther from Earth and closer to the Moon than any human has been in more than half a century, while also supporting science and biomedical investigations that inform future missions. This gives the mission a dual identity. It is a technical test, but it is also a renewal of human presence in deep space. The spacecraft gathers engineering data. The crew gathers lived experience. Procedures are validated, but so are human rhythms, sensations, and judgments far from Earth. The farther frontier, therefore, is not only where machines prove themselves, it is where a generation gap in human exploration closes. So the mission's final meaning is not that human beings go far once more and then stop at the fact of going far. The deeper meaning is that the old outer boundary of crude flight becomes usable again. Artemis II turns lunar distance from a historical achievement into an operational region. It confirms that Orion can carry and sustain a crew in deep space, that SLS and Orion together can execute the complete outward and homeward chain of a lunar mission, and that Artemis is moving from promise toward practiced capability. In the broadest view, this is what the farther frontier becomes. It is no longer merely the farthest line reached in the past. It is the beginning of a renewed pattern of leaving Earth, traveling outward with purpose and returning with knowledge that supports the missions still to come. Now the journey settles into its final proportion. Earth is no longer only the place of departure or the place of return. It is the constant measure that has shaped every stage of the mission, from launch through distance, from the moon's turning pull to the brief and heated meeting with air and sea. The spacecraft has crossed outward into a region where human presence has long been absent, and it has come back carrying proof that the route can once again be lived from within. The crew has seen the homeworld shrink into a small bright sphere, and then grow again into the full reality of sky, atmosphere, gravity, and water. In that long outward and inward arc, distance has become something more than a number. It has become a way of understanding how narrow the human shelter is, how carefully it must be extended, and how much patience is required to move safely beyond it. The moon has remained what it has always been in the night sky, a quiet companion to Earth. Yet from the path of Artemis II it has also become a turning place, a world near enough to fill the windows and strong enough to bend a spacecraft home. Orion, small against the size of that journey, has served as a sealed and temporary world of its own, carrying light, air, water, heat, work, rest, and human thought through the wide silence between planets. Nothing in the mission has needed hurry in order to be significant. The meaning has come through sequence, through precision, through the steady joining of one phase to the next until the old deep space distance has become present again. So the farther human journey doesn't end as a burst of triumph. It comes to rest in a quieter truth. The path outward still exists. The road back still holds. The distance between Earth and Moon is once again a human distance, measured not only by machines, but by breath, sleep, observation, and return.